Hello, everyone. Just recently, we've talked quite a bit about nuclear fission, fission. This process where you're taking very large elements and splitting them up, in the process, releasing quite a bit of energy. Now, we're going to talk about another important concept that's somewhat related, the idea of fusion, FUSION. So, for nuclear fusion, instead of splitting one large atom, you're joining two small atoms. In fact, typically, if we're talking about like the sun, we're talking about some of the smallest atoms, hydrogen. The concept is the same though. Once you join them, you're going to release quite a bit of energy. We can look at the life cycle of a star to figure out what's going on. Typically, we start out with this stellar nebula. This is a great big cloud of gases. And over time, gravity pulls this gas together until eventually it gets tighter and tighter and tighter until it gets hot. And it gets so hot that you actually start this process of fusion. It is several thousand degrees. If it is a little bit of energy, or the average amount of energy, you end up with an average star, such as our sun. Eventually, all of the hydrogen fuses together into helium, and the process begins again, and a red giant forms when the helium fuses. After that happens, for this average-sized star, it will eventually collapse into a planetary nebula once all the fuel is spent and turn into a white dwarf. For a massive star, once it gets to the end of hydrogen fusion, then helium fusion will occur, and then more elements will fuse after that until eventually we get to the super red giant, which collapses again until it becomes a supernova. This is one of the most massive explosions that the universe knows. After the supernova, it will either collapse into a neutron star, or if it's even more massive, into a black hole. So a star like our sun, as it's doing this fusion process, where the hydrogen atoms are fusing together, it will give off huge amounts of energy in the form of EM radiation. If you remember our presentation on energy and matter, you'll remember that that radiation can actually travel through space and reach the Earth. It reaches us as all different kinds, but the Earth's atmosphere can block a great deal of it, which is good for us because we really don't want the gamma rays to be hitting us. We do get a little bit of the ultraviolet light, and that's why when we go outside in the summer, we sometimes need to wear sunscreen. To review, the nuclear fission is where you have these large uranium atoms splitting up. This is what we use for nuclear energy in our nuclear power plants. And the atomic bomb, such as the one we dropped on Hiroshima and Nagasaki during World War II. Now, we have bigger bombs now called hydrogen bombs, and these are actually fusion bombs. What they are is you have a fission bomb surrounding a fusion bomb. The fission bomb heats the core up so hot that the hydrogen fusion is able to occur, creating a second explosion that's even larger. That's why we talk about hydrogen bombs as being more powerful than the traditional atomic bomb. Fusion is powering the sun in this way. And I'd like to point out something that I like to use to remember what fusion and fission is fusion uses this U, which matches well with the U in sun. If that helps you remember, then that's great. Fusion with a U is what powers the sun with a U. We have deuterium, which is basically just one type of hydrogen, and tritium, which is another type of hydrogen. And they come together, they fuse together. This only happens under extreme heat and pressure, but we have that kind of heat and pressure on the sun. They come together and you have now two protons which means it's helium, and 3 neutrons. But those 3 neutrons is fairly unstable, so one of the neutron gets kicked out, and you end up with helium and 1 neutron. And the other big component is energy. And as you might remember, that's because a little tiny bit of our mass has actually been converted into energy. In fact, this reaction is more powerful than the fission reaction that occurs with uranium splitting. Also, something that's really great about this reaction compared to that reaction is you don't have these radioactive isotopes that come out. So you might remember that with the fission reaction, you end up with things such as krypton, but it's not just any krypton coming out, it's a very radioactive form. So you end up with a lot of radioactive waste. With a fusion reaction, you end up with helium and a stable form of it that is not radioactive. All right, that concludes this lesson on fusion. If you have any questions, please ask me in the morning.